Welcome to another lecture on W211. In the last lecture, we have started the analysis of the circuits that contain the energy storage elements. And in that aspect, we started with the first order circuits that contains only one energy storage element in it. And that is either an inductor was connected there or one capacitor was connected in the circuit containing the resistance only. We further stated that the transient analysis has a lot of dimensions, and it is wise enough to start with the circuits that contain only the inductor and the resistance first, and thereafter the capacitor and the resistance. We also studied that going in a stepwise approach is a better approach in understanding and grasping the and building the foundations of the transient analysis of the circuits. And therefore, we decided to split the transient analysis into two parts. One was the natural response, where we suddenly disconnected the energy sources from the system, whereby we disconnected them from the sources. Thereby, they actually transferred the stored power into the circuit. In the second phase of this transient analysis of the first order circuits, we shall discuss the step response of a circuit. A step response is when we suddenly connect a source with the circuit that contains the energy storage elements. In that way, analyze the behavior of an energy storage element when it is getting charged from the external source. So let us start with the step response of the first order circuits. Let us analyze an RL circuit where the energy source is connected with a network containing the energy storage element, and where we do not have any initial conditions, which means that we do not have any current which is flowing in the inductor. So let us draw the circuit and see how we can actually derive for the expressions of the step response of a first order circuit. So suppose that we have this voltage source available here. This is Vs, and we have a resistance R. We have a switch which will be closed at time t equal to 0, and then we have an inductance here. This inductance shall have some voltage in this particular direction, and we have a current that will flow here right after we will turn on the switch, and there will be some current I that will flow after we will turn on this switch at time t equal to 0. So the value of the current IT is actually of an importance for us, and therefore we will try to hunt out and we will try to expand an expression that can elaborate us the value at any given time instant t if we plug in the value of the resistance R and L, inductance L, and this voltage source Vs. So notice here that we shall not see any decaying exponential here. The current will rise from some initial value to some final value, and at that final value, which is after we will elapse the 5 time constants, the final value will be decided solely by this resistance R and this voltage source Vs. So the inductor will eventually become short circuit after time t is equal to 5 time constants, and that will show us the steady state response of a given circuit. So let us start with this numerical here. So to solve with this particular numerical, we will use the circuit analysis techniques, right, to derive the expression that describe the circuit in terms of the variable of our interest, which is the current across the current through the inductance, and the voltage across the terminals of this particular inductance L, and then we will use the mathematics to solve that particular equation. So in this given circuit, at time t equal to 0, the switch is closed, which means that the circuit will become of this particular shape here. So we have, again, this is VL, this is L, this is R, and we want to see what is the current IT here. This is Vs here. So if we apply the Kirchhoff's voltage law in this closed path, then we have Vs equals to VR plus VL. Notice here that the voltage across this resistance, which is this VR, it is defined by the Ohm's law, which is equal to I into R, and the voltage across the inductance is governed by the expression which is given as L di over dt, This particular expression is explained in detail in the lecture where we introduce the inductor and the capacitor. So we have to solve for this particular current I of t, and thereafter we will move on to the solution of the voltage across the given inductors. This equation is the starting point of our analysis, and we shall actually use it for the rest of the analysis. So this particular equation can be written as di over dt is equal to Vs minus I of R divided by this inductance L, right? And that is equal to minus R over L I minus Vs over R. And if we solve for this derivative di over dt, we will get the expression for the current at any time instant t, right? After the switch is closed. So that is the goal, is to solve for this differential equation for this particular value of it. So to do so, let us first of all multiply both sides by dt. So this will eliminate this dt from the left hand side of the equation. So I am left with only di, and that is equal to minus R over L I minus Vs over R into dt. And thereafter we can actually separate the variables. So this becomes di over I minus Vs over R, and that is equal to minus R over L dt. So now we need to integrate both sides, and we can use the separate variables for the integration. Let us say we have x and y as the variables of the integration, and let us integrate them. So if we integrate this one, so that will become equal to I naught I of t x divided by x minus Vs over R, that is equal to minus R over L 0 to t, this is equal to dy. Notice here that this I naught, this represents the initial current or the initial condition of the inductor, because we have earlier stated that this I naught is equal to 0. So for that particular circuit we shall put the value of I naught equal to 0. But to make a general approach to solve any circuit, whether we have some current flowing through the inductance or whether or not we have some current flowing in the inductance, we need to specify this I naught as an initial condition or the initial current which is flowing in the given circuit. And this I of t, which is this particular upper limit of this integral part, this it is actually the amount of the current at any time instant t. So we can, if we solve for this particular equation, we will be able to get the value of the inductor current at any time instant t. So let us integrate this one and see what we get as a result. So this become equal to, so this equation, this will be of the shape log of it minus Vs over R divided by I naught minus Vs over R is equal to minus R over L into t, right? So now this particular portion can be written as e raised to the power minus R over L into t with a log here, right? So if I take a log here and I write log e raised to the power minus R over Lt, then this natural log will be cancelled out with this natural log, thus leaving behind only this particular value, which is the it minus Vs over R divided by I naught minus Vs over R, and that is equal to e raised to the power minus R over L into t. Notice here that if I further manipulate this particular equation, and if I further address this particular equation and I do some sort of mathematical arrangement here, I will get the value of it, that is equal to Vs over R plus I naught minus Vs over R into e raised to the power minus R over L into T. Now, for this particular circuit, if the initial condition is equal to 0, likewise, in this particular circuit, where when we draw the circuit, we stated that the initial condition current is equal to 0. So, for this circuit, if there is no initial current flowing in this particular circuit, which should be obvious because we cannot allow a sudden interruption of the current. So, it means that if we have some initial current flowing here, then the circuit might be connected with some other network. But from this particular circuit, it seems like that this inductance is actually having no current flowing through it prior to the switching at time t equal to 0. This means that if we have, for this particular circuit, if we say that the initial current I naught is 0, this means that I0 negative is equal to I0 positive, that is equal to 0, which means that the solution of the current IT is now reduced to this particular equation minus R over L into T, right? So this is the expression of the current that governs the behavior of the inductor if it is connected with the energy, if it is connected with the sources. For instance, we have used the source Vs here, right? So this is the equation that derives the expression, the behavior of the inductor. Now, after we have now turned on the switch, so let us say we have time t equal to at time t equal to 0. What will happen at time t equal to 0? I of t will be equal to Vs over R minus Vs over R, and that should be equal to 0, right? Because there is no current which is flowing here. So if I plug this t equal to 0, then e raised to 0 is equal to 1, which gives me Vs over R, and Vs over R is cancelled. So IT right at time t equal to 0 is equal to 0. And this shows the property of an inductor which opposes sudden change in current. And therefore, I0 negative is equal to I0 positive is equal to 0. So if I plot it for the time instant t, let us say this, we have IT here, and this is a time t here, and we have let me redraw the circuit here. We have this particular network. So let us graphically see how the things move on as we turn on the switch at time t equal to 0. So we have this resistance R, this is the voltage source Vs, and this is the voltage across the inductance VL, and here we have some current flow that should flow after time t equal to 0. Now prior to the time t equal to 0, which is I 0 negative, the current was equal to 0 because the switch is open and there is no other initial condition that exists here, which means that at time t equal to 0, the inductor will try to retain the amount of current that it was holding before. But as soon as we have the time elapses, we have a transient part that will vanish with the passage of time, and thereafter the current will settle at a value which is governed only by this resistance R and this voltage source Vs. So let us say that the final value of the current after all the transients will vanish out, the value is equal to is this particular value. Let us say this is equal to Vs over R, right? And we have a zero current which was flowing here. This is the zero current which is flowing here. Now the current will rise exponentially and it will reach this particular value at time t is equal to 5 tau. So this is the 5 tau constant which is required for any first order circuit to reach the steady state value. In this particular condition of this first order circuit, the final value is actually the current which will be determined by this resistance R and this voltage source Vs. So we have at 5 time constants, we have this Vs over R. Now notice here, just like we did for the natural response of an RL circuit, if I draw a tangent here, so if I draw a tangent here, then the point instant at this particular time instant is the 1 tau. Notice again that this is not drawn to the scale, and therefore you have seen some sort of a discrepancy here, that we have the 1 tau that is taking too much time, and then we have 5 to right here. So let us say that this is not to the scale. However, it is quite evident that as soon as we have the current flowing through the inductance, the voltage across the resistance becomes larger, and as a result the voltage across the inductance becomes smaller. Now we know that the current cannot change instantaneously, and therefore it will try to retain its zero value. However, it will eventually be able to reach the steady state value after the 5 time constants. And we also notice here that the point where we have one time constant, we have almost elapsed the 63% or 64% of the final value, which is equal to Vs over R. Right? Regarding the voltage across the inductance, now we do know what is the value of IT. So the voltage across the inductance VL is equal to L di over dt, and therefore the voltage across the inductance is equal to L into minus R over L into I naught minus Vs over R e to the power minus R over L to T. That becomes equal to Vs minus I naught into R e to the power minus R over L to T for T greater than or equal to 0 positive. So you see here that the voltage across the inductor will shoot instantaneously to the value which is equal to Vs at time t equal to 0. So if I may draw a line here with this highlighter, then this is the voltage line. Okay, so this is the voltage line. So after the voltage jumps to the value which is equal to Vs, let me draw this one as this is equal to Vs. The voltage will eventually become equal to 0 at after time 5 time constants. Now this is quite an obvious response when it comes to the circuit analysis here. So notice here there are two very important points. At time t equal to 0, which is this particular instant, the current is 0 and the voltage is equal to Vs, and this is the voltage across the inductance. So let us see how it is actually happening here. So let me draw the circuit again. So we have this Vs, we have this resistance R, and this is the circuit at time t greater than or equal to 0. So first of all, let us see what is the initial condition here. So the initial condition is I0 negative is equal to 0, and because inductor do not permit any instantaneous change in the current which is flowing through it, therefore I0 positive is also equal to 0, right? Which means that the voltage VL, which is equal to Vs minus VR, where this is the VR, and VR is equal to I into R, right? So at time t is equal to 0 positive, which is time right after we have turned the switch on, the current is equal to 0, and consequently this whole part becomes equal to 0, and therefore VL instantaneously jumps to the value which is equal to the source voltage Vs, and as a result we have seen that the voltage waveform of the inductor will have a shape which is which at the first sight do not look very convincing. So let us say we have this is the voltage. So we have a sudden jump here, and then we have this type of a voltage here, and at time t equal to 5 tau, the voltage across the inductor will become equal to 0, which shows that the inductor has now come into a steady state condition, and therefore the inductor will act as a short circuit to a DC network. We do not have any rate of change of the current here, because the current which is supposedly moving like this particular point here. So we have after this particular point di over dt becomes equal to 0, and consequently the voltage across the inductance become equal to 0, and thereby it becomes a short circuit path for the device. So the only current which is the current limiting is happening because of the resistance which is involved in this given circuit. So the voltage will jump instantaneously to a value which is equal to Vs, and thereby it will follow the decaying exponential as governed by the expression of the current which is here. So the time constant tau is again a decisive factor in designing or in describing the charging and discharging of a network where we have the inductance available here. The step response of an inductance will have a shape which is not of a decaying exponential, rather it will be a rising exponential up till a point where it will become equal to the maximum value, which is set by the value of the resistance R and the value of the voltage source, which is V. Let us draw another circuit here. Say we have this particular circuit here. We have a switch here at position number 1, and we have switch with a possibility to move to position number 2. Here we have the resistance, and here we have the inductance available here, right? So now this is quite obvious that if the switch is given a high logic, it will be at switch number 1. If it is given a low logic, it will move on to position number 2. So we have switch at position number 1, we have switch at position number 2. So the if we draw the timing diagram of this particular circuit now, then the current through the inductance will be of this particular shape. It will rise something like this one. It will drop like this one, then it will again rise, and it will again drop, right? So this is how the inductor current will actually see. You will visualize the inductor current if there is a constant switching of this particular switch at some fixed frequency. So the inductor will require a finite time for the current to become short circuit, and thereby we see this exponential here, and this exponential becomes equal to its steady state value, which is governed by this resistance R and this voltage source Vs. So let us say this is equal to Vs over R. So the inductor current I, which is shown in this red line, it shows that the current requires some finite time to reach the final value Vs over R. And after we provided a zero logic to this particular switch and we moved it to this position number 2, then we see the natural response of the circuit. Thereby, because it is turning off for enough period of time, so therefore all the energy which is stored in this particular inductor is dissipated in this particular resistance in the same fashion like we discussed for the natural response of a shorter circuit. So we have we see a decaying exponential here till the point we reach the 5-time constant. So we can say that this is the time which is the 5-time constant for the charging phase, and this is the time instant for the 5-time constant for the decaying exponential. But both of the time constant R over L over R is decisive in developing that instinct whether or not a circuit is in a steady state condition or not. In this particular case, it is now coming in a steady state condition. You will notice in the advanced classes, maybe after a few semesters, that this sequential switching is based on some electronic switches which are used to develop the H-bridge circuits. And this RL circuit actually is very useful in modeling a basic concept of the winding of the motors, like the stepper motors, or for the DC motors, or for the induction motors. So we have actually developed a basic instincts. If you see that you are applying some switching pulse like that, and the current is actually having a rising slope, and then we have a decaying exponential, this means that the circuit has inductance in it, and that it is actually behaving like a first order circuit. So depending on the value of the time instants and the value of the 5-time constant, we see that the sudden connection of a first order RL circuit with the source is effectively, it happens in the same manner like we dissipate or like we deliver the stored energy of the inductance to the circuit elements. So this is for the inductance. Let us see what happens if we have a capacitor with us, right? So for the step response of an RC circuit, let us say we have a circuit here. So for the ease in mathematics, let us say this is the current source IS. We have a resistance R, and here we have a switch that will be turned on at time t equal to 0, thereby connecting this capacitor with this particular source IS and this resistance R. So we have some voltage here. Let us say this is VC, and we also assume that VC 0 negative is equal to 0. So we do not have any initial condition for this circuit as well. So VC 0 negative is equal to 0, VC 0 positive, it should also be equal to 0, owing to the property of a capacitor that it do not allow any instantaneous change in the voltage across itself. If I say that this is a node A, and at time t greater than 0 we turn on this particular switch, thereby switching it something like this one. So we have closed this switch. This is time t greater than 0. So what will happen now, that we can actually apply the KCL here. So KCL at A yields that IS is equal to this IR, which is the current through this resistance, plus IC, and that is equal to V over R plus C dVC by dt. And we notice that because all the three branches are connected in parallel, so I can also say that this is equal to VC over R. So this can be written as dVC over dt plus VC over R is equal to IS over C, and this is exactly the shape that we have discussed for the step response of an RL circuit. So this can be solved without going into the mathematics. We need to substitute few variables in the equation that we have derived for the inductance, and thereby we will get the exact solution for the voltage across the capacitor, because here we have this voltage available here. So what we are going to replace, we will actually replace the IS. We will replace them with this Vs here, and also this C with this inductance L, 1 over R with the value of the resistance R, which was previously used to derive the expression of the current through an inductor against the step response of the first order circuit. And this V naught, we will replace it with this I naught. So if we do this for the voltage here, then this Vt is equal to Is into R plus V naught minus Is into R e to the power minus T over RC, and this is valid for t greater than or equal to 0, right? So if we do not have any initial condition, that is we have V0 negative is equal to V0 positive is equal to 0, then this equation simply becomes equal to ISR minus ISR e to the power minus T over RC, where RC is the time constant of this particular circuit. Now again, if we draw the capacitor voltage and the capacitor current here, so the capacitor voltage will require some finite time to reach its final value, and that is equal to Is over R. This is the final value of the final value is equal to, which is equal to Is into R. This is the final value of the capacitor voltage, and the before, because we do not have any voltage across the capacitor, therefore the capacitor current was equal to 0. But right at time t equal to 0, the capacitor current will become equal to the value of the source current, which is equal to Is. It will actually have this particular type of a slope here. So we have an instantaneous jump in the capacitor current as soon as we turn on the switch at t equal to 0. And this is obvious because if we see this particular circuit, we have a current source here, and we have this resistance R, and here we have a capacitor here. So we have turned on this particular capacitor, which has Vc equal to 0, which means that this particular capacitor is acting as a short circuit path, and therefore all the current which is supplied by this current source will be diverted through the capacitor. Instead of going through the resistance, it will go through the capacitor, and therefore the capacitor shall have a value which is equal to Is at time t equal to 0. And this is permittable because there is no bar on the capacitor to not allow the change in the current. Capacitor do allow in any change in the current at any instant. It could be instantaneous, like we have seen here. However, it do not allow the instantaneous change in the voltage, and therefore this voltage source waveform is governed by the expression which we have explained here, right? So it will have a value which finally the capacitor voltage will become fully charged. As a result, the capacitor current will become equal to 0, and therefore the capacitor will behave like an open circuit, and thereby all the current Is shall flow through this resistance R only, right? So this is how we have seen the criteria to develop to understand the step response of the first order circuit containing the inductance and the first order circuit containing the capacitances only. We shall in the next lecture we shall see the general expression to derive the to derive the expression for any first order circuit. So we shall see that in the next lecture alongside the simulation part. Till then, in the next lecture, take care. Allah Hafiz.